How you doing? It's been a while since we've talked, so as a reminder, I'm Mr. Rose. I used to teach you physics, and today we're going to keep talking about static electricity. I'm going to try and do this a little bit quick. I'm going to give some directions as I go. Feel free to, write some stuff down if you'd like. This is going to be kind of some calculator work, so it's not going to be the most fun stuff. But we're going to start talking, specifically about Coulombs Law, what that actually is. So I did keep my bad noise effects or sound effects here. Watch this little animation. It's very quiet. All right, we've all had that before. Now in this animation, again, all these animations are not fantastic. There are protons on a doorknob. A doorknob is made out of metal. There are also electrons on a doorknob. That's important. This animation obviously doesn't show that. But when you walk across, say, the carpet or something like that, you can pick up extra electrons. And what we learned out of the sticky tape are all neutral objects, like the doorknob, will attract any charged object, like you, if you picked up all those extra electrons. So when you touch the doorknob, you get that little shock. Now we're going to talk about really what, there we go. Really, how much force do you feel in that? Or the force, it's not really the force that you feel, it's the force that's attracting that charge to you. So we're really going to talk about the force between the charged objects, between the positive charges that were on the doorknob and the negative charges that were on your finger. And to do that, we're going to talk about Coulombs Law. Now, Coulombs Law, as it says, depends on several factors. It depends on the charge. Now, the charge we represent by the letter Q, and if the doorknob had charge, and you had charge, that would be a doorknob, that would be you, and the distance. Now, this distance is represented by an R or a D. It depends on our equation. I've used D in all of our equations. I just forgot to change this one. But in a higher level class, you'd often see that as an R, for a radius. But it's really just the distance between two objects, and then some constant. Now, I never tell you to ignore units. Units are important. There's this electrostatic constant. We don't really need to know a whole lot about that, but essentially that is the ability to have that shock take place. It's the best way we can describe it right now. The actual number, 8.99 times 10 to the 9th, we can use that. Often it'll be rounded to 9 times 10 to the 9th, and we'll get pretty much the same answer. We'll go over some scientific notation again. And then the units. I want us to look at the units. The units are Newton, because that's the unit of force. Then this meters squared, well, that's because there's a distance involved. And then if we remember the unit for a charge is a coulomb, and a coulomb squared. So if I look at meters squared, that means I need to take a square of a distance somewhere. And if I look at coulomb squared, that means I'm going to multiply those charges together to get a coulomb squared. Now, you might be thinking we did something similar to that in the past, and we did. We'll see that in a moment. So Coulombs Law is this electric force, that's what this little E stands for, the force electric, or the Coulomb force, sometimes it's called, is equal to this electrostatic constant, K, times charge 1 times charge 2, divided by the distance, how far away they are, squared. So when you got zapped from the doorknob, if you're really far away, there's no zap. If you're really close, there's a big, there's that zap. If there's enough charge, say like a cloud to the ground, there could be lightning bolts. And I'll post some videos about lightning as well. Now, to calculate Coulombs Law is going to be a little bit complicated. But again, we should have seen something like this before. Do we remember when we calculated force? Remember, everything's got a gravitational force. These two things look really similar, and they should, because Coulomb actually came up with his law based on observational science, what we knew about universal gravitation. Because if we remember our planetary model of our atoms and all those things, we mimicked what we knew at the time. So it seemed to make sense, and it works because nature is symmetrical isn't the right word, but nature, it just works. We're going to leave it at that. Sorry, that's a bad explanation. So we've done this universal gravitational constant, mass 1 times mass 2 divided by d squared. We saw Peter Griffin and his orbit. Electric force is the same exact idea, which means as objects are really close together, the force is really big. Objects get further and further away, the force gets smaller. The bigger the charges, the bigger the force, just like the bigger the mass is, the bigger the force. Now, there is a difference that we'll talk about a little bit later on. This is what we were just talking about, the inverse square law. The bigger the force, the closer they are, the bigger the force, the further away, the further the force. Now, the difference is gravitational forces concerned with mass, and that is a property of matter just like charge. The Coulomb or the electric force is based on charge. Now, which one of these two forces is stronger? Now, we're going to go through this calculation. I recommend you try and calculate, use a calculator on your own. Remember powers of 10. If I wanted to write, say, I'm going to show you right up close, 8.99, then I want to get to the powers of 10. You probably can't see that, but I'm going to press that times 10 to the n button. And then I have a times 10 to the caret, because that's what I want to be. I don't want to be in math print. And I'm just going to write 9. And now if I want to keep multiplying things, I'm going to put a parenthesis, and I can keep my multiplication going. So I'm going to consider two objects that are 5 centimeters apart. I'm going to calculate the gravitational force, and I'm going to calculate the electrostatic force between them. Now, the objects I'm calculating are 2 electrons. These are not numbers you need to memorize. But an electron has a mass of 9.11 times 10 to the negative 31. So if there are 2 of them, that is universal gravitational constant, 6.67 times 10 to the negative 11th. 2 electrons, 9.11 times 10 to the negative 31 times 9.1 times 10 to the negative 31, divided by how far they are squared. Try and do all of that in your calculator. Then come down and do the electric force. 8.99 times 10 to the 9th, again, a number you don't need to memorize. That's on the MCAS sheet. 1.6 times 10 to the negative 19th coulombs. If you remember, that's the charge of 1 electron. And if I'm doing an electron separated by 5 centimeters, or 0.05 meters, it would be an electron divided by the distance squared. So we've done these calculations before. I have the answers for you, and you can see both are really small. This negative 66 newtons is a super small force. This negative 26 newtons is a super small force. But comparing the two of them, 26, 36, 46, 56, 66, that is 40 orders of magnitude, or 40 powers of 10. That's how much bigger this electric force is. Now, you may have noticed an electron is supposed to be a negative 1.6, but since I'm just looking for the magnitude of the force, I don't care about those negatives. So we can see that the electrostatic force is way bigger than, I can move that, hey, there we go. The electrostatic force is way bigger than the gravitational force. Now, if I did protons, my numbers would be exactly the same, except the mass of a proton is different than the mass of an electron, so this gravitational force would be the same, but the electric force would be the exact same. I said this gravitational force would be the same. It'd be different because these masses would be a little different. Now, one quick example, or I should say another example, 2 more examples actually. What is the electrostatic force between 2 objects if I have a charge of negative 3 coulombs and positive 2 coulombs? I just plug that right into my equation. Oh, and I gave a distance of 2 meters. Now, these are totally made up. Now, notice when I have a negative charge and a positive charge, a negative times a positive is a negative. We know opposite charges attract. So this force is going to be an attractive force. When I put everything into my calculator, I want you to try this as well. Don't just look at my work. Try this in your calculator. You should get a force of negative, oh, I messed up here, negative 2.69 times 10, that should say times 10 to the 10th, not to the 10th. So that is negative 2.69 times 10 to the 10th. This negative force means it is an attractive force. Those 2 objects are going to attract towards each other. So it is an attractive force. Now if I look at the next one, what is the electrostatic force between these 2 objects? A negative and a negative. Now this little m, that's a micro coulomb. That's just a really, really small charge. If I separate it by 5 nanometers, so this is more accurate, or more, not accurate, this is more realistic because it's a really small distance. I put that all into my equation. The microcoulombs are times 10 to the negative 6. The nanometers are times 10 to the negative 9th, so this is harder for you to do on the calculator. But what I want to show is a negative and a negative is a positive value. those objects are going to repel. We know that. And I get a positive force, 3.6 times 10 to the 15th newtons, and it's a positive. That positive means they're repulsive. Now, this is the other difference between the electrostatic force and the gravitational force. 3 differences. Bam, I'm zoomed in now. 3 differences. It's super important. Difference number 1. The electrostatic force is much, much bigger than the gravitational force. Difference number 2. The electrostatic force deals with charges. The gravitational force deals with mass. Both fundamentals of matter. Difference number 3. The gravitational force, check it out, falls down. Falls down. Almost dropped my coffee. This is super light. Falls down. The gravitational force is always attractive. No matter what, unless Oprah's around, no matter what, you are going to fall and be attracted to the Earth because the Earth is really, really big mass. The electrostatic force can be attractive or repulsive. That's all I have for you to talk about in this video. That was a long 10 minutes. That's actually 11 minutes now. That is the end. You can look at my desktop. Feel free to leave any comments you want, ask any questions. I am going to post a worksheet that goes with this, and I'll post going through an example or two as well. That's all I have. I hope you all are enjoying the day. It's actually kind of nice today, although I don't know when you're going to watch this. Charge up to do some physics. Yeah, puns, dad jokes. I'll speak to you all soon. Bye.